So hi everyone. I'm just letting you know we'll be starting in a minute or two.
Hi, folks, and welcome to the third lecture of the Categories for AI lecture series. Today we have a lecture by Bruno. He was the lecturer in our first installment. He's a PhD student in Glasgow, where he uses category theory to try to understand machine learning and game theory. Take it away, Bruno.
Thank you, Joao, for the introduction. Hello, everyone. I'm very excited. First of all, thanks for sticking to the third week, and I'm very excited to tell you about something we're calling categorical data flow and how we can use category theory to shed light on various computation patterns that are happening in neural networks, including backpropagation. So this lecture is supposed to last about 2 hours, including QA. There is a lot of ground to cover, so I will just get started. Please do feel free to ask any questions that come up. But yeah, so before we start, I want to just give a recap of where we are. So in the first week, we've given you a high-level idea of what category theory is as a unifying language, sort of allowing us to find patterns that are usually otherwise impossible to detect. And in week 2, we've started to substantiate these claims with some concrete definitions. So I'm going to go through some of these concrete definitions just to refresh your memory, just so we're all on the same page, and then we're going to build more and see what more we can do with those. So we started and we finally gave in the first week the definition of a category. So if you remember, a category is something like a network of relationships. So we can imagine we have some objects in our category, some entities we're studying, and we're studying the ways they are related. We usually draw these as arrows. And that's essentially what it is. It's a very simple concept. And one might confuse it with the notion of a graph. So you might think a category is like a graph. And it's true that it is like a graph, but there are some differences. So I'll just remind you that these four axioms here written are something that a category needs to satisfy, and it's what differentiates it from a graph. So category has objects and morphisms, and something we require in a category is and that's what category theory is all about, it's composition. So if we have a morphism from B to C and a morphism from C to D, then we require their composite to be also a morphism. Likewise, something we require is to have identity morphisms on each object that need to satisfy the last two rules written below. These rules are basically coherence conditions telling us that identity behaves as we'd expect. When we compose it with anything, we get that morphism, and that composition is associative. So that's what a category is, and we went on to define a number of categories, and something that's maybe the most important thing to realize and to sort of realize in our intuitions is that categories, that objects and morphisms can be various sorts of things that aren't necessarily sets and functions. So for instance, there is a category called set where morphisms are functions and objects are sets. There's a category rel where objects are sets, but morphisms are now relations. Likewise, we can have a category of where objects are vector spaces and morphisms are linear transformations. But really, objects in a category don't need to be sets. For instance, we could have a category here called boldface R, where objects are numbers. So let's say 2, 3, 4. And a morphism, there's only one morphism, and it exists if then one number is smaller or equal than the other. So this is the kind of intuition we want to give you, is that categories can have objects and morphisms as very strange things and very general things. And we mentioned the category group, which we think of as a single object category, and this is really a group where morphisms are group elements. So when we defined these categories, we can study many kinds of constructions inside these categories. And I'm not going to go through them, but just to remind you, we talked about monomorphisms, epimorphisms, products, coproducts, exponential objects, and so on. So I'll briefly remind you of one of these concepts just before we go into actually the meat of the topic today, which we'll see what it's going to be. So just to remind you, we talked about products, and in a category, we define products as following. So we might have some object A, we might have some object B, and if you remember, we defined a product to be another object called A times B. So it's another object in this category together with projection morphisms, which we may call pi of A, pi of B, such that for any other candidate product, we have a universal arrow mapping that candidate product into what we've called the product. So this is the slide from Petar's talk, sort of elaborating what this was. We've likewise talked about coproducts, which were the same story, but exactly with arrows reversed. So you might remember we talked about a coproduct of A and B is another object, which we denote now with the symbol plus, A plus B, with injection arrows, which I might call inject A and inject B, such that for any other candidate, we have a universal morphism going out of it. I will not stay too much on this definition, but sort of the main idea I want to give you is that these concepts are entirely dual and can be defined in terms of each other. So we've seen structures inside these categories, and we talked about functors. So I'll briefly just remind you that if we have a category C and a category D, each of which has some internal structure, some morphisms, and some objects, we talked about a way of mapping between these categories. So the same way inside categories we have objects and morphisms, you can think of categories as sort of objects, and then morphisms of categories are called functors. This is another slide from Petar's talk giving particular axioms that these functors need to satisfy, which I'm not going to go into right now. With the main idea being that every sufficiently good analogy is yearning to become a functor, as famous category theorist once said. So after this very short interlude reminding you of what we've done, I want to emphasize that what we've done so far in these 2 weeks is we talked about categories, and we described how they talk about sequential processes. We've seen some commutative diagrams and some arrows say F going from A to B, B going from B to C, and we talked about ways of composing them. So these are sequential processes, but as you know, being in deep learning and neural networks, the kinds of systems and the kinds of processes we study are very complex. They are first and foremost, they're parallel processes. They don't just have morphisms that are plugged together in a line, but as you see in this figure from a particular paper, we often have morphisms which sort of copy information. We have morphisms with some information, and it's not clear so far how do we study all of these things in the language of the categories described so far. Likewise, the essence of why deep learning works is backpropagation, where we have kinds of processes which we don't just have a morphism from A to B, but that morphism has a forward and a backward component. So there's lots of intricate structure happening inside deep learning, and the question is, can category theory really describe that? Likewise, today we're going to have a very hint of probability. We're going to briefly mention how we can start thinking about probabilistic structures. So this is the lecture plan for today. We're going to answer all of these previous questions using category theory. So we're going to see how to model parallel processes using something called monoidal categories. And we're going to talk about their graphical language of string diagrams. We're going to then, since this is quite a bare bone structure, we're going to talk about how to add bells and whistles to this monoidal categories, ability to copy information, delete information, sum it up, cross strings, and we will see that this is reminiscent of interfaces that we have in software engineering, where we specify upfront what kind of interactions are possible to have for a given object. Then we're going to see how to study parallel processes using Cartesian monoidal categories, and more specifically, deterministic parallel processes. And once we've done that, we're going to look at how bidirectionality works, how we can model backprop, and much more general stuff than backprop. Maybe the most interesting thing that we're going to see is that lenses, in an abstract way, and I'm going to tell you what lenses are, model the chain rule. So as I said, we have a lot of ground to cover, so I might just get started with this. So we will start with monoidal categories. And the main idea behind monoidal categories is that they describe parallel processes like the one you see here on the screen. So this is pretty straightforward, and this kinds of diagrams is something that I'm sure you've seen in many different places. And it's certainly very easy to read. So we read this as going from left to right, and we read a box as a process that in this case takes a lemon filling and prepared crust and fills the crust, for instance. This is a very silly example in a way, but it tells us what monoidal categories are. They describe parallel processes, and they are a formal system, a formal language for thinking about this. Really, they originated quite a few years back with Roger Penrose and his graphical notation for tensor networks. Since then, this language has been generalized and appropriated and started to be used in many different disciplines. So as I said, we're going to think about objects in a category as strings and morphisms as boxes. But really, before I go into the definition, I want to sort of draw a bit and get you a sense of what we're trying to do. So we've seen so far how to talk about, we've drawn some morphisms from A to B in our category, and we can imagine perhaps drawing it as a box like this. And I really haven't given you a formalism so far for talking about parallel processes. And what I want to show you now is how, if we just start thinking about it and try creating that formalisms ourselves, that monoidal categories, their definition, which is on the next page, is going to come out naturally out of thinking about the geometry of the plane. So the definition is going to look scary, so I'm trying to lead you into it. So we can imagine having one process and drawing it on the side as a box and some strings. And if we have another process, say going from C to D, which I'm going to call G here, we might be tempted, and I'm going to draw the same process here as a box. We might wonder how to think about these two processes as one process. So note here, I've drawn literally two processes which have, each of them has a domain and codomain. And we're thinking of them as separate. But if we're aiming to think of these processes as a morphism in our category, so as some sort of arrow, then that entails choosing a particular domain and codomain of that process. And since we're trying to put these processes in parallel, we might write something like this: A times C, B times D, and here we might write F times G. This is precisely what the idea of monoidal categories are, which I'm going to make precise, except that we draw this arrow as a X with a circle around it. And this is often called the tensor product. Sometimes people say A tensor C or F tensor G because it started from a particular branch of math. But we might posit that this is something we can draw in our category. And what I want to draw your attention to is that what we've done so far by merely drawing another morphism with this domain and codomain, we have defined a functor. So we have defined a functor that starting from some category C, and the product of C itself goes back to C. So what does this functor do on objects? So if we have an object A and an object B, well, we've defined, it seems like, sorry, I'm going to call this C. It seems that we have defined the action of this functor to take A and C and map it to a particular object which we have called A tensor C. Likewise, it seems like we have taken a pair of objects B and D and mapped them to another object which we call B tensor D. And likewise, we've taken two maps and considered them as one map. So if this made sense so far, you're well on your way on understanding what a monoidal category is, and it's something that involves this functor. As I've said, monoidal categories capture the geometry of the plane. So another thing that we have to think about when turning, so the idea is we want to turn this pictures into formal mathematical objects. And when we think about the plane, we don't just have morphisms, but we also have the empty space between the morphisms. And this is captured by something we're going to call a unit of our monoidal category. So we're going to denote some object to denote the empty space in between our morphisms. And if you follow so far, this is part of the definition of what a monoidal category is. So I'm presenting it here. A monoidal category is a tuple of many things. It consists of a category C, a functor called the monoidal product, which joins objects in a particular way, and a sort of a neutral object called the monoidal unit. Now, in category theory, we always see that we have some structure, and we have that structure obey particular laws, particular coherence diagrams, telling us it behaves the way we'd expect it to. So, for instance, I told you that the monoidal unit 1 is a particular object that represents the empty space, which means that we'd expect having an object X in parallel with the empty space is isomorphic to just the object X. Likewise, we might expect doing that from the other side is going to give us the same X. Another thing we might want to expect is that if we have many objects, say X tensor Y, tensor Z, we might expect that to be isomorphic to X tensor Y tensor Z. So we want to ignore the way, the order these things are applied, or at least track it and say that this is isomorphic. And if this made sense to you so far, well, you're on your way to actually understanding what a monoidal category is, because the 2 points that I introduced here are something called an associator and the left and the right uniter. So this is reminiscent of things in high school algebra where you want things to be associative, or multiplying things by 1 gives you the same thing. Now in category theory, we don't say they're the same, we keep tracking them using isomorphism. Now, this might seem like a lot of data right now, and it might seem quite confusing. But the idea of a monoidal category is to take the visual intuition of the plane, the geometry of the plane that we all know and can easily manipulate in our heads, and write it down as explicit algebraic data that we can encode and prove properties about. So we'll see that this takes the best of both worlds, because when we need to think about monoidal categories, we're going to draw these string diagrams, which I'm going to talk about. But when we need to prove things about them, we can have concrete structure to refer to. And if somebody gives you a monoidal category and claims that it is a monoidal category, you can check rules and axioms of these categories that tell you whether that really is a monoidal category. So you have a systematic way of checking it. Now, there is a last component of this monoidal category, which is on the next slide, which tells you that these associators and these uniters have to behave in a particular coherent way. So it might look quite scary here. Basically, we have 2 axioms here telling you that if you, and these are commutative diagrams, as you might remember from the first lecture, this is how we call them. So here we were saying that the right uniter, associator, and the left uniter all behave coherently with respect to each other. 1 second. So they behave coherently with respect to each other. And likewise, the second diagram tells us that the associator can be applied in a particular way and interacts well with the monoidal structure. Now, this all might look quite scary, and it's something to think about. It's certainly not something that we expect you to understand right now. the point of these axioms is that it precisely specifies the geometry of the plane that we're interested in. So when we think about and we draw these diagrams in the way I have, we can be sure and we can precisely say what kind of transformations are or are not allowed. And we can precisely say, when somebody gives us a monoidal category, whether this is truly a monoidal category. So it's a systematic way of thinking about it. So to really show you what I mean by this, and this is, I believe, one of the questions was in the chat about this monoidal product. Why does this need to be a functor? So monoidal category has a lot of structure, and I'm going to focus on one particular bit and show you how it gives us some graphical intuition about what's happening. So you might remember that if we have a category from C to D, and I'm just taking any normal any functor between them, you might remember that this functor needs to satisfy this equation. So if I have here I have so let me just draw these morphisms. I have A, B, and C, and let's say I have two morphisms F and G. Then this functor is going to map A to F of A, B to F of B, and C to F of C, and this morphisms to F of F, and this is going to be mapped to G of F. Now, a functor needs to satisfy particular axioms that you might remember, one of which is this one. So F of F composed with F of G should be the same as F of F composed with G. By the way, just a slight note on notation. You might have seen previously people use the notation G after F to denote the composition of F and G. Here in this lecture, we're going to use something called the diagrammatic notation, which is quite useful when we think about string diagrams, which is often denoted by this. So F composed with G is going to be noted like this here. So what we see here is something that a functor needs to satisfy. So the question of why does the monoidal product need to be a functor can be unpacked to the following question. We are going to study what does functoriality of this tensor, I'm going to often call this tensor, I'm often going to call this tensor, we're going to study what functoriality of this means. So if you remember, for a standard functor, this needs to hold, but for us, so let's write, we had AB, I'm going to write CD, maybe I'll write it like this actually. So we have A, E, C, D, E, F. So our objects are going to be pairs, and a morphism here is going to be pair of functions. Let's call this F of A, F and H. Let's call this G and I. Then unpacking what functoriality is going to tell us that first applying F to a morphism, which is going to be now a pair of morphisms, and our F is tensor, means F tensor H composed with, and now applying F to the second component, which is going to be G tensor I, should be the same as applying F to the composite, which is going to unpack to F composed with G tensor H composed with I. So this is the equation that needs to be satisfied for this monoidal for this functor describing a monoidal category. So what does this equation mean when we draw it graphically? So I'm going to take this, I'm going to copy it, and I'm going to paste it here in this slide. So remember, we had morphisms from A to B, and then a morphism from B to C. And then we had another morphism from D to E, from E to F. That's correct. So I'm going to write here. So this was F, this was G, this was H, this was I. Now, what functoriality of this functor tells us is that it doesn't matter which way we evaluate this, which way we box this product. So we can do either this. We can compose the morphisms, like we're doing on this right side, and then pair them and consider them one big morphism. This should be the same as first considering them individually, paired up using the monoidal product, and then composed. So functoriality tells us that this should hold. And what this allows us is that when we see a diagram composed, so let's say we just see a particular diagram like this composed out of some arrows, it doesn't matter what way we think about it, what way we box objects and morphisms together. We know that our theory follows from that. And any sort of visual manipulations we do, we can translate them back to the algebraic theory, useful for implementing in a computer and really thinking about in terms of many other constructions we have in category theory. So this is the idea of these string diagrams and monoidal categories, is that we can translate back and forth between equations and morphisms in a monoidal category down to the graphical language. And we can transform things up to planar isotopy in this graphical language and still get a valid equation in the language, in the equations that we had before. So to get a sense of what this means, I'm gonna and before we really go on into seeing examples of monoidal categories, because there's many, I just want to have a question maybe for the audience, if you can write in the chat, in a monoidal category, which of these diagrams are equal? So some of these diagrams can be transformed into others, maybe all can, maybe none can, and then they are considered equal as morphisms in a monoidal category. And the question is which diagrams are equal. I see some answers. I'm gonna wait a bit more before proceeding. So I see many answers. I think one, well, nobody's definitely being sure in their answer. But let me help you out saying one part of what is equal. I can certainly tell you that 1 is equal to 2. Now, why is that the case? Well, I think this is pretty easy to show. We can imagine taking this k, and we see that this k was slid through here up to this position, right? And we see that we haven't really been crossing any wires when we went between these two diagrams. So that's certainly the case. But now, and the last bit what I'm going to tell you is why we're being very strict about these axioms, why there's so many equations and things happening in a monoidal category, is because the third diagram is not equal to 1 or 2. So this is not equal in a monoidal category. And this is because in just a bare bone monoidal category, I did not tell you how to cross wires. So it is not possible to get this k, and this is really the issue, right? We can move this guy around and this morphism around, but the problem is that k is inside the other morphism, and we can never get it out. There is no way there's no way to get out the k. So just to remind you, I said, just to remind you what the previous slide was, morphisms are equal in a monoidal category if in the graphical language up to planar isotopy, they are equal. And we can see that planarly, we cannot move K in any way out of this little encirclement. Okay, so let's get some examples of monoidal categories, just to give you a sense of how this works. So maybe the most canonical example is the category set with its Cartesian product as the monoidal product. So this would be set with the Cartesian product as the monoidal product, which means that in the category set, I can draw a morphism like this, say, and write here x, y, and write z here, call this f. And as a morphism, we interpret this as a morphism from x times y into z. This monoidal category has a unit, which is the one element set. So what this means is that you might remember some equations. This means that if I take x times 1, this should always be isomorphic to x, and so on. And this is certainly the case. Taking a product of anything with 1, it does give us something isomorphic to x.
Bruno, just people have some
yeah.
questions that I think should be answered now instead of continuing. So one of them is the geometry or position contain information in addition to the information, the morphisms themselves?
So is the geometry position containing information? I will interpret this question as meaning
they elaborated with concretely y is k in a square followed by j in a square different than j first and k second.
So let's see, y is k in a square followed by, so where is different than the j? Sorry, I'm trying to parse this question. We see k in a square here, which is a morphism. So maybe I should be clear about that. This is a morphism in a monoidal category. And here we have a morphism j in a monoidal category. And here we have a morphism h in a monoidal category. We see, so for instance, we can translate the morphism h. Let's label the wires. This could be x, this could be y, this could be z. So for instance, h, and let's say these are in a category maybe set, for now thought of as just a monoidal category. This would be a morphism from z to y, right? And then j, this is maybe important to mention, j would be a morphism from z times y to the monoidal unit, because there is nothing drawn. If you remember, I said monoidal unit is the empty space. So this is going to be 1. So I'm trying to understand the question and unpacking it. Why is k in a square followed by j in a square different than j first and k second? I'm quite not sure what that means. Maybe this can be elaborated further. I might even suggest getting this question for the end of the talk. Maybe this question is going to be elaborated in the meantime. So I would, if this is okay, I will continue and answer it at the end of the talk. And if it's really not clear, maybe just to get a better understanding of what this is, we can even follow it up on Zolip. I would be very happy to do so. But just to elaborate here, so this would be the types of morphisms. And to be absolutely clear, the type of morphism K here would be of 1 into 1. And now, if we write this as a composite, if we write the whole thing here as a composite using equations, you will see that there is no way to take that as a symbolic equation and transform it into something of this shape. None of the equations of a monoidal category will allow you to do that. Okay, so moving on, we've seen the category set with the monoidal product, and we've interpreted the product as times. So we take both an X and a Y. But the monoidal product can be much more general. It doesn't have to be times. It can be, for instance, plus. It can be the disjoint union. So if I tell you I have the category set with a disjoint union as the monoidal product, then the same diagram drawn, X, Y to Z, this would be F, would be interpreted as F from X, sorry, I'm going to write X disjoint union Y, this is Y, into Z. So really what I want to make precise here is that I have to tell you what monoidal product I have on a category. So not, if I just tell you the category, it could be ambiguous which monoidal product I think of, because there could be many monoidal products on a particular category. As we've so far seen, we have the category set with its categorical product and co-product, but both of these are monoidal products. Now, the terminology here might sound confusing, but it does get easy once you sort of get the hang of this. And so we've seen that even though products in a category are unique up to isomorphism and co-products are unique, both of these are just special cases of monoidal products. So I'm going to march on and maybe spend just a little bit of time on this exercise. I think some formatting got messed up here. This should be R, the boldface R. So category with multiple monoidal products, if you're maybe math oriented, is the category of vector spaces, where you can consider the tensor product as the monoidal product and the biproduct. I'm not going to spend too much time here. It's not terribly important, but I thought I would just mention it because we have an audience of quite diverse backgrounds here, so it might be important to mention. Another example is the category of relations that we have seen. So you might remember the category of relations. A morphism from A to B is a relation, which means an element here might be, and if this is a relation, an element might be related to another element, right? And this category has a monoidal product defined as follows. So if we have another relation R, and let's call this P, and this goes from C to D, we can form the monoidal product of these relations, which on objects, it's given by just the Cartesian product on objects. So B times D. And we can form a composite relation. I'm going to call this Q, where, Q, if I have AC, Q, BD, is defined to be true if and only if A is related to B and C is related to D. So the point of this example is to really show you that monoidal products take a very general form that captures a number of examples. We're going to see a one more or maybe two more which are directly related to us, but I just want to remark on some of the questions which are, I see some questions in the audience asking about the geometry of the plane. I think this might become much clearer once we get a bit into the course and start talking about symmetric monoidal categories, because we're going to have the same question back up again in a different setting. And I think if it's still not clear, then we can raise that thing. Now, another example of monoidal category is monoids. We're going to actually talk about them quite a bit in this course. I'm just going to briefly remind you what a monoid is. So if you have any set, let's call this X, we call a monoid, we call X a monoid if we have some operation called, I'm calling it here times, which goes from X times X maybe I'll just call this set A so it's not as confusing, which goes from A times A into A, and we have a neutral element 1 of A, such that this is associative, and for any A in A, we have that A times 1 is equal to A, or 1 times A is equal to A. You might have seen monoids. I think people are coming from a lot of different backgrounds here. Monoid is quite pervasive in mathematics, so you might think of real numbers as a monoid with addition, so you can add things and then 0 is the neutral element. You can think of real numbers as the monoid with multiplication and 1 as the neutral element, where you can multiply things, and if you multiply with 1 you get the same thing. Very interestingly, if you're doing functional programming, you might know of monoids as an example of a monoid, a list of a particular type. So if you have a list of, say, numbers, list of natural numbers, then a list of numbers 1, 2, and 7, you can concatenate this. I'm going to write this plus plus in the Haskell notation with a list containing 4, 5 to give you a list 1, 2, 7, 4, 5. That is interestingly a monoid, where the empty list is the neutral element. So Booleans are a monoid in many different ways, and function composition, I'm going to actually skip this one for now and come to it later, but this is also a monoid. So the whole idea here is that monoids are, first of all, pervasive everywhere, and there are special kinds of monoidal categories where you have no morphisms. So if you've seen this, this might be an interesting example of what monoidal categories are. But the one that's maybe the most interesting for machine learning is the category of Euclidean spaces and smooth maps. So this is a category where objects are things of the form R to the n. So it's an n-dimensional Euclidean space. And a morphism between Rn and Rm is going to be a function that is differentiable, and we can specify, do we want it to be 1-time differentiable, 2-time differentiable, and so on. But for us, we can just even consider infinitely differentiable if we want to. So this is a very interesting category, which is monoidal, which means that if I have two differentiable functions, I can pair them up. So if I have Rk to Rl, this is G, I can literally form a composite Euclidean space where I run both differentiable functions in parallel. So this is an interesting example because it's going to come up later quite a bit. One other example is the category of Markov kernels, which you might know about. So this is, I'm going to introduce this category quite briefly right now, just because for two reasons. First of all, to show you that in category theory, we can have non-deterministic structures. But second of all, to show you how this is going to be quite relevant later on when we talk about bidirectional transformations. So if you come from maybe thinking about Bayesian learning, you might have seen these things. So for instance, the category fin-stock is a category where objects are finite sets. So for instance, I have a set X. And if I have another set Y, a morphism between it, let's call it F, is a Markov kernel, which we think of F really being as a matrix of X times Y. So, you know, if satisfying particular rules. So I'm going to write this here. And before I tell you the rules, I'm just going to write a simple matrix. Let's say we have a 2x3 matrix. Then how we interpret it is that for each input, and there's two possible inputs, we have a probability distribution over the output. So for instance, we have 0.1 that we're going to get the second output, 0.6, and 0.3 here. And if you get the second input, you might get 0.4, 0.4, 0.2. So this is a category, and where morphisms have to satisfy this rule. So so it's the case that for each x in x, we have that the following holds. So f. So by the way, I should tell you that the notation we use for these kinds of morphisms is we write f of y given x, and then we want the following things to hold, that for all y, f of y given x, the sum of all y's is 1. And we also wanted to hold that for all y, this is always bigger than or equal to 0. So basically allowing us to interpret this as probabilities. This is a whole area of study, so I'm not going to spend too much time of it, other than to tell you that the way you compose two morphisms is something that's, if you're familiar, this is called the Chapman-Kolmogorov equation, really just multiplying the corresponding matrices together. The whole point being here that this is a category, so it satisfies associativity, unitality, but this also is a monoidal category, whose monoidal product implements stochastic independence. So if I have two morphisms, let's say F, two Markov kernels, one from X to Y and another one from Z to W, I can form a composite morphism going from X to Y. So on objects, I take the Cartesian product. And on morphisms, the way I form the composite morphism is by the Kronecker product of matrices. So this is also a monoidal category. And we can see that with this kind of constructions, we can model relations, we can model non-deterministic processes, we can model sets, we can model vector spaces and linear transformations, so a number of different things. Okay, so I've given you actually quite a bit of examples, and all of these have a lot of structure. Now, but an arbitrary monoidal category doesn't necessarily possess the structure. And the question is, and quite related to maybe the questions in the chat, what can't we do in an arbitrary monoidal category? So again, it takes, once you start doing category theory and thinking about monoidal categories, it takes a while to understand what each of the axioms are doing. But I want to just give you a quick rundown of some of the things you might think you can do, but you can't. Or at least you have to be upfront and specify that you're in a particular kind of setting. So in a monoidal category, in an arbitrary monoidal category, you cannot pass strings through each other. So for instance, if this is something that you can do, if you can pass them through each other and consider like nothing happened, you are in a setting that's called a symmetric monoidal category. The reason for this distinction arises really in math. In many settings, you have these things where this level of nuance is quite needed. For many things in computer science, you often want to work in a symmetric monoidal category, which is why I think lots of people in the chat sort of really tended to braid these wires together and to say, oh, I can slide things through each other. It really depends what setting you're in. So in category theory, we're being quite stringent about that. Likewise, in an arbitrary monoidal category, you can't copy information like this, and you can't just delete information, right? So you have a string going like this. You can't just say, well, it's going to stop. If you want to do that, you have to be precise and be upfront about the kind of interface you're using, the kind of computation you can have. Likewise, if you want to add strings in some particular way or start them from nowhere, you also have to be upfront about that, and this is going to be something called a supply of monoids. So the idea here is not to disallow anybody from doing anything, but merely to be upfront about the interface we're using. So we're taking a really stringent and rigorous view here of what kind of computation you can be doing. And if you think about, in computer science and software engineering, we have classes and interfaces. When we write a class, we say what are the kinds of things we can do. We are going to have inheritance and whatnot. And these are the only things we expect the user of our interface to be able to do. So the same goes for these things. So I see the questions like, what does passing of strings represent in symbolic terms? I'm going to answer that right now because I'm going to unpack what a symmetric monoidal category is. So a symmetric monoidal category is a monoidal category, and I'm going to call it monoidal category C. So it has all the structure we talked about, equipped with an additional thing. It's equipped with a morphism, which I'm going to call sigma. Maybe I'll draw it better. Sigma, which for each object x tensor y gives me swaps the argument. So this is sigma, and it's defined for every pair of objects. So every x and y, we have a morphism that does this. So really, in an arbitrary monoidal category, we might not have this morphism, but in a symmetric monoidal category, we do. And as always, whenever we introduce a new piece of machinery, we have to say how it interacts with all the structure we've had so far. So this particular equation satisfies some laws. So it satisfies the law that if I start from x and y, and maybe I'll draw this here on the side because I think it's useful to have. So if I start from x and y, and then I swap them, so going here, I swap them, this would be drawn like this. And if I swap them back again, so I'm going to swap them back again, getting x and y, we have an equation saying, well, if you swap it and go back, that's the same as not having done anything. And this is an equality, really. It's identity. And we have some other axioms telling us how it behaves with respect to left and right unitary. So for instance, if I have x times the empty space, which is here I, and I swap them, then it doesn't matter so remember, the row is going to be x tensor I is isomorphic to x. Lambda is going to be I tensor x is isomorphic to x. So these need to hold. And likewise, we have some more telling us how it interacts with associativity. Yeah, I have the question. Yeah, so this is equality after swapping. Yeah, that is true. Okay, so we might wonder, if being symmetric seems quite as a natural thing, and you might wonder why do we all bother with monoidal categories? And I'm going to give you one example of a monoidal category that is non-symmetric. So you might remember from the first lecture this notation as notation for the exponential. So when we write this, I will recall this for you. This really means the set of functions from x to x, where x is some set. So this is really a set here, and you might remember this being a monoid from before. So let's first of all remember let's try to understand what this means. This means that if I give you a function f from x to x, and I give you another function g from x to x, I can form a composite which is going to be called f composed with g, which is another function from x to x. So this is really a monoid from before, and we know that composing any function with identity gives us that same function. Now, very importantly, this is a non-symmetric. So first of all, this is a discrete monoidal category, doesn't have any morphism between it, but it's non-symmetric because F, composing F and then G is not the same as composing G and then F. So this is a quite interesting example to realize that symmetry is not something we don't always have. Okay, so there's a lot of grounds we're covering, and now we're coming maybe to the question that I hope will help clear up. And I'm going to ask which of these diagrams are equal in a symmetric monoidal category. I'm going to also take this opportunity to have a read through some of the questions. I've seen there's lots of stuff happening that is quite hard to catch up with. So again, to restate the question, which of these diagrams are equal in a symmetric monoidal category? Yeah, so the answer by Samuel, I see all of them, and that is correct. So from before, we know that 1 is equal to 2. And now with the added notion of symmetry and crossing of the wires, we know that we can slide K out of this hole, right? So we're saying in our interface, we have the ability to do so. So we know that K can be slid out, making it equal to both of these. And likewise, I've shown you that this can be unpacked. This can be untangled. Can I actually... this can be untangled to just straight wires, allowing us to show that it is equal to this one and therefore the other ones as well. So yeah, all of the diagrams are equal here. So there's a question from Dobrik: if symmetry was not present, would 4 be different? So I see there's quite a lot of confusion here. I also want to mention that what is presented here is quite a simplified view, because we, in between monoidal categories and symmetric monoidal categories, we have braided ones, in which case this would hold, but this would be different than these two. I've skipped over that, but I'll just let you know that this is something you can look up. This is also from this particular lecture notes, from categories in quantum informatics, where we might link this because it gives a quite thorough elaboration of why this actually holds. But okay, we've done a lot of work and we talked about lots of monoidal categories, but let's try to understand where we're trying to go. So recall I told you about neural networks and the idea of copying and deleting information and parallel processes. This is where we're trying to go. But so far, I've only told you about monoidal categories and only told you about putting processes in parallel. As we see here, there's lots of other things we can do. So I'm going to briefly talk about symmetric monoidal categories with supplies. So you see what's happening in the course. We're slowly building more and more structure. We started with categories. We said we can put them in parallel. We said we can cross some wires. And now we're going to say, okay, we can do particular kinds of things. We can copy, we can add information. And we're going to see later that this level of generality is going to allow us to uncover some really new kinds of things we can do with neural networks. So the two examples we're going to study is the supply of comonoids and monoids. Really, we're going to focus mainly on this one for reasons that I'm going to explain now. But before I start that, I'm just going to also briefly recall what is a comonoid. Now, if you've been listening to this course, you've heard about the notion of duality and how we make things very simple in category theory by flipping the arrows. So that's exactly what's going to happen here. We can dualize the notion of a monoid and get something called a monoid in a very straightforward way. So let's remember what a monoid was. It was a set with some operation A times A into A. And it was a choice of a neutral element. Now, before I've written this as 1 as an element of A, but if you remember Petar's first lecture is we don't like to talk about elements. The way to talk about an element of a monoid is really as a map. So I should be maybe very precise here, as a map into A. And if you remember how we talked about this before, this was a map from the terminal object, which unfortunately uses the same notation 1 here. So this is an object, a set with 1 element, and we're going to choose some map. Maybe I'll call this N for neutral, some map that picks out the neutral element of A. Now, to get a comonoid from this, we were going to simply reverse the arrows. So I'm going to have a comonoid. It's going to be some set. Let's call this B. It's going to be some operation. I'm going to call delta like this, which goes from B to B times B. And we're going to have some operation which goes from B into the terminal object, which I'm going to call T for reasons that might become clear if you've been following carefully. So a comonoid is something that has this data obeying the analogous laws of associativity and unitality. What is an example of a comonoid? What does this mean? Well, if we're in set, really our hands are tied because remember, in set, any map into the terminal object is uniquely determined. What this means is that it takes any element of B and just ignores it, maps it to the unique element of 1. It forgets information. And likewise, the laws of associativity here are going to force our hand that this map is going to really, the only thing it can do is it can take an element of B and copy it. So the idea of comonoids that we're thinking about is something that allows us to copy and delete information. And this can be formulated not just in set, but in arbitrary categories. And this is something we're going to see right now. Now, in category theory, the thing we study often is not just, I'm going to write this T, is not just comonoids, but also comonoids homomorphisms. We're studying structure preserving maps. So if you have a comonoid B, and let's call it a comonoid G with plus, sorry, no, this plus, going to call this, I'm gonna subscript them so we know this is, sorry, this should be delta B, this should be G, and this should be TG. We might wonder what is a comonoid homomorphism. So a comonoid homomorphism is going to be a function from B to G, and I'm going to call this F, such that particular diagrams are satisfied. And it's sort of the only thing that can be satisfied. So we're going to have this function F satisfy the following rules. If we go from B and then copy B and then apply F twice on the result, that should give us the same thing as applying F and then copying the result. This has a natural interpretation using string diagrams. And I invite you to bear with me for a second, where I hope all of this will become clear, why we are doing this. So we're unpacking this structure, which is going to help us understand what kind of things we might have in neural networks. So remember, we are in a monoidal category, so we can draw this as diagrams. So we might draw F like this, which takes some set B. And then we might draw the copy operation like this, saying we apply F and then copy the result, getting 2 Gs. And we are positing that this is the same as, well, first copying the input B and then applying F twice. Likewise, we have another equation that our morphism F needs to satisfy, which is that it has to interact well with the terminal maps. So I'm going to write TB, which means that if we start from B and then use the terminal map TB to delete things we've had, well, we should get the same thing if we used our map F to get to G and then deleted it. T. In a graphical language, that means this. If we started, so maybe I'll do it like this. If we started from B and deleted it, this should be the same as starting from B, applying F, and then deleting our information. Now, why am I telling you this? Because it seems almost absent-mindedly by just unpacking these equations, saying this F needs to agree with all the structure that there is. We've uncovered deterministic maps. So if a map is a comonoid homomorphism, it is deterministic. Now, what does this really mean? The best way to understand what determinism is to see what it is not. And if you look at the previously mentioned category of Markov kernels, Finstock, which talks about probabilities, and given every element, we have a probability on its outputs, there's a very simple way to understand it. Rolling a dice and then copying the result is not the same as rolling 2 dice. This is the main idea. This is not an equation that holds in Finstock, because we'll see this is not a category with a homomorphic supply of comonoids. But we'll see that various other categories that we've had, set, vect, and I should also add uke, the category of smooth spaces, does have this supply. So the whole idea of this very maybe unpacked ordeal is that we can slowly, in the language of category theory, start to say all the things we know about. We can talk about copying information. We can see when processes are deterministic or not, and we can slowly start to have this very expressive language. And as maybe cherry on the cake, if you have a category with a homomorphic supply of comonoids, that gives you exactly a category with products. So this is a very interesting theorem that tells you any symmetric monoidal category where you can systematically copy and delete things is isomorphic to the category theoretic product that Peter mentioned here. So this is quite an interesting result, and allows you to think about this. Why I like this, because it gives us an operational characterization of this category, of the category products, and allows us to think about these tangible things of copying and deleting information. I'll just have a look. I see lots of things happening, so I might have to take many questions towards the end. It's quite hard to catch them on now. So I'll briefly ask here in the chat, and I think this should be quite easy if you've been following or if you know about the idea of duality, is what would a homomorphic supply of monoids on a symmetric monoidal category give us? Is there any thoughts? So yeah, this is actually something I'll leave you to think about, and just give a sense of where we've gotten so far. So we've talked about parallel processes, we've talked about crossing of strings, and we've talked about copying and deleting of information. Now recall this with the addition of monoids, which I actually skipped here. It gives us the basic building blocks to start talking about morphisms, very complex kinds of architectures and morphisms in neural networks. We now know how really to form these building blocks. If we are in, say, the category of Euclidean spaces, we can form a morphism of this particular type. We can talk about the way it copies purely from the level of category theory without needing to sort of invoke low-level things. Of course, when we implement things and when we think about them, it's useful, but what's useful is shifting this level of abstraction. And from a personal standpoint, what really ended up being interesting is that once you formulate this at this level, formulate neural network learning at a very abstract level, you start to find many interesting things. So some of my co-authors discovered that the same categorical constructions that tell you how to differentiate, something we haven't talked about, differentiate and study neural networks or on Euclidean spaces, it's the same, exactly the same structure to do learning on Boolean circuits. So I learned that you can differentiate Boolean circuits in a meaningful way. And category theory allows you to talk about this in a uniform way and then say, well, I want to specialize to this category for this setting, say the category of Euclidean spaces, or I want to specialize to this other category for the setting of Boolean circuits. And there's many other categories that need to, and how do we know which category which we can specialize to? We specify these things up front. We specify the axioms, we specify the things that are needed and the interface that we want. I invite you to have a read through this paper. Okay, so we've done quite a lot of things. Before I go and maybe answer this quite provocative question, I'll answer one of the questions that seems to be quite really upvoted in the chat, and I think it might be something quite useful to say. So there was a question: would it be possible to show how you would interpret these diagrams as arrow composition and monoidal products? So this is something I'm going to just briefly remark on right now. So let's say I have a diagram like this that I've written in some monoidal category. So there is a map F, produces a Z, and then I have another arrow that takes a W and produces M. So this is a string diagram that I've drawn for a monoidal category, and the way we would draw it as an equation would be as follows. So we would write, so first of all, we would look what is on the left side, what are the inputs? So this would be X tensor Y tensor W. We can look at what's on the output. This is going to be M. To be absolutely precise, I'm actually going to take care of the bracketing because we're going to be interested in first using X and Y together with F. So these are going to be our domain and codomain of our morphism. As we draw this morphism, we're going to draw it as a composite whose intermediate object is going to be Z tensor W. So what's remaining to fill is what morphism is this and what morphism is this. The morphism on the right side is going to be G, because we see G takes Z times W into M. And on the left side, it's slightly more complicated. We see it's going to be F, but we also see we're going to have in parallel an identity wire on W. So this is going to be written as one W. So I hope this clears it up.
For the next question, Sishu asked, is there a way to learn what category you're trying to work on? So I guess the idea is, given the data set you have, the format structure, whatever, and what you're interested in, is like, how do you know what category to use to model it? And he gave a more concrete example. So given a symmetrical monoidal category and non-symmetrical monoidal category, is there a way algorithms differ between the two? I think that's
so. Yeah, I'll say that understanding and trying to learn, which category we're trying to work on, it sort of works the other way. When we think about the systems, we set the category, right? So we're trying to set what kinds of things we're trying to study. So we would like to say maybe we would like to study processes where we copy information, where we delete, and so on. Maybe you're talking about trying to understand some particular phenomena, and you're trying to figure out what kinds of categories should you model it with. For instance, is it a Cartesian category? And then one of the things to check, for instance, let's say you have something, you have a category which is monoidal, and you're wondering whether it's Cartesian, whether it's given by the product structure. So one thing you could check is you take a morphism and you check whether this equation holds. You check whether copying the output of a morphism is the same as copying the input and then applying the morphism twice. I see the answer is about learning this. I'm actually this is a much more complicated process. And I think this is something we'd love to actually have at one point, neural networks to discern this kinds of structure. But so far, neural network seems to be really operating on sets and not really like very structured data. Well, we have graph neural networks in these recent days, but having this very highly structured data that satisfies some particular axioms such as associativity or unitality, it's really unclear at this point. So this is definitely a very big and open area of research. So yeah, given that I see that we're quite short with time in a way, there is quite a lot of interesting things to do. I'm just going to go right in and remember that other than just modeling networks that copy information, add information, have all these sorts of parallel processes, we are interested in modeling systems that have a forward and backward components. If you think about backpropagation, this, and look up any tutorials, it's notoriously an interesting thing to explain and has so many different perspectives. And we might wonder whether this is modelable in category theory. So the answer is going to be yes. And it's going to be modeled using something called lenses. So I'm going to go right in. What is a lens? So a lens is something of the following shape here. It models a deterministic bidirectional process. So it's something that has, we're going to see here, a forward and a backward part, and a particular flow of information. It's going to be modeling all sorts of different bidirectional processes in a uniform high-level way, the same way we've seen so far. So before I go into the definition, I might even just copy this and have a look at it here. So a lens is a particular gadget that has two ports on the left side, two ports on the right side, where we think of this port as input, this one as output. So this could be values, this could be gradients. And then we're going to have values go forward, as it is in a neural network. We're going to save some intermediate state, and we're going to have gradients flow backward. So a lens is going to consist of a forward map, and it's going to which is here called get. In the lens terminology, we might use the terminology get. We might also often use the terminology view. And it's going to consist of a backward map here called put, but I'm going to refer to it in a more evocative language, update. So a lens consists of a forward map view and a backwards map update. And how lenses work is as follows. So unlike so far where we defined a category and said, this is the kind of structure it needs to satisfy, for lenses, we're going to do something else. We're going to say, hey, give me any Cartesian category, any Cartesian monoidal category. So this is a category where it's a symmetric monoidal category. We have comonoids on every object, and all morphisms are deterministic. Give me any such category, and I can give you a category of lenses. Then you might ask me, how do I define this category? And it works as follows. So we can define a category lens C whose objects, and now this is an interesting thing, and objects are pairs of objects in C. So this is a category where objects are pairs. So here we have an object A and an object A prime. And these are both objects of C. And now what is a morphism in this category? So if I have an object in lens, which is going to be a pair of objects, and another object in lens, which is going to be a pair of objects, a morphism is still going to be a pair of morphisms, and I'm going to call them view and update. View is going to be a morphism from A to B. You can think of this as the forward part of a neural network. It takes some A, produces a B. And update is going to be the backwards part of a neural network. So it takes an A, it takes a change in B, called here B prime, and produces an A prime. So we see here. So this is a category. I've defined objects, I've defined morphisms, and what I now have to tell you is how composition works. So if I have a lens from A to B and a lens from B to C, sorry, when I say A, I mean AA prime, BB prime, and a lens from BB prime to CC prime, it just gets quite unwieldy saying. I'm going to define a lens, a composite lens going from AA prime to CC prime. How am I going to do that? Well, to do that, I need to tell you what is the forward map, what is the view map. So this is going to be a map from A to C. And how am I going to define it? Well, I can use the view 1 or update 1 map for the first lens and the view 2 and update 2 map of the second lens. So this is going to be defined as follows. The composite, so this is going to be, let's say, the composite map view, and this is update. The composite map view is going to be defined as view 1, and then I'm going to have view 2 after this. So view 1, view 2. So this is pretty straightforward, but it becomes quite tricky when I have to define the backwards pass of this lens. So the backwards pass of this lens is going to be something of the type A times C prime to, and I'm going to draw it far right here, A prime. So it is A times C prime to A prime. The way we're going to define this is as follows. I'm just going to make this a bit more careful. To define this composition, we're going to work backwards. And this is in line with backpropagation. It goes, we're going to think about, well, how can we produce an A prime here? So this is what we have to do. And if we look at all the things we have, well, we see that the only way to produce something that produces an A prime is the map update 1. Well, this, this has to be a part of the solution, update 1. If it's not, then we're in a problem, right? So we've reduced our problem of defining A prime to the problem of defining, of getting an A and a B prime. Okay, so to get an A, well, we already have an A, that's good. But to get a B prime, well, let's look again. What do we have here? Ah, right. The only thing that produces a B prime is update 2. Update 2, and I'm going to write A times update 2. So this is going to be A times B times C prime int. So as you might see, we're slowly working backwards. So we are trying to define this composite update map, and we are defining it in terms of constituent maps of the composite lenses that we have. Okay, so we're getting there. We have A and a C prime. We have to produce this. We see that the only remaining thing is to produce a B. Okay, so now let's have a look. What is the only thing that produces a B? It is the view 1 map. Right. But now we're in a problem. Well, to produce a B, we need to use an A, but we also need to use an A here. Luckily, we are in a Cartesian category, so we can copy the A. I'm going to copy the A and keep C intact. So this is going to be A times C prime. By the way, I thought I would just also mention something we do in category theory is often when I write here A, I mean, sometimes I would write A when I mean identity on A. So this would be identity on A. Since in category theory, everything is about morphisms, sometimes we really just take the shorthand instead of writing the identity, we equate it with the object. So this really here means identity on A. This here means identity on C prime. Okay, and now we're getting quite close. So from this to get to this, we really need to just apply view one on the middle A. So I'm going to write identity on A times view one times C prime. Okay, so this might seem like a very long and arduous process, and it might be quite, you might be wondering why we're doing this. Well, before I explain the crescendo of this, I will just give this formula in a very, hopefully straightforward form, where we're going to write it like this. The composite view is going to take an A, and it's going to compute it. I'm going to write it in terms of variables. So it's going to apply view 2 after I apply view 1 to A. And the composite update, which is going to take an A and a C prime, you know, we can write it as equations, is going to do the following. Well, it's going to call, so before I actually write this, I might make it easy for all of us by just copying this so we can have a look at this. So I'm going to rewrite the update map in a slightly more manageable form. So this is going to be update 1, A, so we see I'm also working backwards, update 1A, and then it's going to be update 2 of A view, sorry, update 2 view 1A C. This might be quite useful to try to understand how in the category of sets we can take any commutative diagram like this and write it as its action on elements. So we see we take an A and a C prime and we do this particular thing. And we see the copied A is appearing twice. That's why, because we copied it. Okay, so we defined lens composition. I'm going to leave this exercise here, mainly for you to try to understand where did we use the fact that morphisms are comonoid homomorphisms. So I've told you that C needs to be a Cartesian category, Cartesian monoidal, which means that every morphism is deterministic. That is, it's a comonoid homomorphism. Where did we use it so far? And we can answer maybe later in the Zulip. This might not be quite easy to prove where this is used. So what I want to give you now is some examples of lenses. And the most central example, which was the most interesting to me, is to learn that derivatives are lenses. So let's say I give you a function that takes a vector, and I'm going to take a vector of two elements, x1 and x2. Let's say it computes 3x1 squared plus 7x2. We all might be familiar with the fact that we can compute the gradient of this function at a point x1, x2 as a matrix. That is the Jacobian. And of course, when it's a gradient, it's going to be really a vector because it's much simplified, but we can still think of it as a matrix, and it is going to have the following contents in it. It's going to be 6x1 and 7. Now, the central observation that derivatives are lenses arises if we realize that the matrix is really a linear transformation. So any matrix can be turned into a linear transformation. And since we are often in neural networks thinking about reverse derivatives, I'm going to turn it into a particular kind of transformation with the following type. So I'm going to say this is going to have the type R into R2. So what does that mean? Well, given some change in the output, which I'm going to call here dy, I could have called this whatever I want, it's going to be mapped into 6x1 dy 7 dy. So this is really merely turning any matrix into a linear map. So this map is not just a function, it's additionally a linear function. But now, when we think about things in category theory, we want to not think about elements. We want to make all the inputs really explicit. So let's realize that this thing here, x1 and x2, the point at which we're evaluating the derivative at is also an argument. So I'm going to write this as a type. I'm going to write here r squared, because that's the input here. And then the gradient of f takes two things. It takes x1, x2, a vector, takes a change in the output, and produces a vector of changes in the input. Here I've written it parallel. Now, if you look at the fact that f is a function from r squared to r, we can see that this is starting to look like a lens. Namely, if we are in the category of Euclidean spaces with the Cartesian product, any function that is augmented with its derivative can be formulated as a lens of this shape. So we're going to have the type of inputs to f and the type of gradients of f, and the type of changes at the input. And here we're going to have the outputs of f. And the view map of this lens is going to be f itself, and the update is going to be the gradient of f. So you can see f goes from r squared to r, and gradient of f goes r squared times r to r squared. Now it might be, you might wonder whether this is truly, what is the purpose of modeling like this? But it magically, I can just skip it. It magically turns out that chain rule arises as a composition of lenses. So this is something that I had a hard time believing myself. But if I give you a function f, which I've defined before, and if I give you another function, let's say cosine, so both of these could be lenses. Let's think of it like this: r squared r. If I augment both of these maps, so this is a forward map and this is going to be the gradient. So I'm thinking of f and the backward path and the gradient of f as a lens. And if I think of cosine, by the way, the gradient of cosine really is going to be a function r times r into, sorry, my pen is breaking up. It's going to be this. So given x and a change in the output, we're going to return sine of x dy. So if we look at cosine and its gradient as a lens, then evaluating the previously defined lens composition is going to compute exactly the chain rule. So let's look at what happens. So I'm going to take this formula that I've had here, and maybe just this part, and show this. So what we're trying to compute here, just to establish, we're trying to compute a composite lens. Now the composite length of these two pieces is going to have the forward part equal to composition of f and cosine, which is going to be just whatever that ends up being. That is quite non-controversial, but the backwards part is going to be quite involved and given by this formula, where instead of update 1, we're going to have the gradient of f. Instead of a, we're going to have x1, x2. Maybe I'll zoom in a bit. Instead of update 2, we're going to have the gradient of cosine. And instead of view 1, we're going to have f. So this is going to be x1, x2. And I'm going to call the output change dy. So this is the same. So maybe I'll just do this. So how do we, let's evaluate this? Well, maybe let's work inside out. So the gradient of f at a point x1, x2 is going to be, well, the gradient of cosine, which is sine of whatever is f, which is going to be 3x1 squared plus 7x2 times dy. And evaluating the gradient of f is going to give us, as we defined it on the previous slide here, with this formula, it's going to take the input vector and give us this. So let's just paste it there so we can look at it. Right, so we're going to get a vector. Basically, we're going to get 6 x1 times dy, and now dy is this. So we're going to get 6x1 times the whole thing. And the second element is going to be 7 times the whole thing. Which I'm just going to put here because there's not enough space. Right, so this shows us that purely through categorical machinery, where I've defined lenses without ever looking at chain rule or differentiation to begin with, I've given you a way to compute it in a very general form. And then it's going to turn out that backprop really can be formulated as a functor from the category of Euclidean spaces to the lenses on Euclidean spaces. So let's briefly unpack what this functor is going to do. So when we, this is what is the essence of automatic differentiation frameworks. So a functor from the category of Euclidean spaces to lenses on Euclidean spaces, and I'm going to call this bprop. It's going to, on objects, take a Euclidean space and map it to a pair of the Euclidean space and itself. And if I have a differentiable function f between them, this needs to get mapped Rm. This is going to get mapped to f and the gradient of f. You see here that if you used set, we couldn't have defined this functor because there's no way to define the derivative of just any function. And you can check that this functor satisfies functoriality and that this precisely is going to capture the idea of the chain. Now, there's many things that lenses model. Since we're quite short on time, I might sort of rush through this, but I really do invite you to ask me later. I would be very happy to answer these questions. You can model gradient descent as a lens. So if you have your parameter space RP, the view map is going to be identity, and then the update map is going to be your standard gradient descent step, which takes a weight, takes some change in the weight, and computes some alpha movement in that direction. It turns out you can model more complex optimizers of lenses. So if you have momentum, which here the first argument we think about as the internal state, the history that is saved by the optimizer. So, momentum saves that accumulates some gradients and then it keeps the ball rolling. There's a more complicated formula, but we can still see that it can be captured as a lens. What's interesting here is that, if you look at how momentum works, it takes in the accumulated momentum, it takes in the current parameter and doesn't do really anything. It just produces that parameter in the forward pass. And then in the backward pass, it computes the change. But then if you look at Nesterov momentum, the look ahead it computes, it's precisely done now in the forward pass that we haven't previously used. So this was quite a surprise to many of us when this was understood. So I've told you, I'm going to give you examples of lenses. If you know automata theory, you might know about Moore machines, which, you think of a machine that computes an output given a state, and it computes an update. It takes a state and some input and produces a new state. This is very trivially a lens of this shape. And there's many more things that can actually be said about behavior and simulating Moore machines one with another. So rushing through, we can do much more about with these kinds of systems. So lenses are a particular way of looking at deterministic bidirectional processes. But really, if you're doing Bayesian updating, if you're doing Bayesian learning or anything probabilistic, you know that we can do all of these things even if the things at hand we have are not really sets and functions, but stochastic maps and Markov kernels. Likewise, if you're actually implementing lenses, you might want to wonder how we implement them in software and worry about some operational aspects of whether it's efficient. So these are all the things that can be done with something called optics, which I am sadly going to have to really dash through. So this is a more general form of modeling bidirectional transformations. And among other things, it includes probabilistic ones. This was the whole reason why you mentioned the category of Markov kernels, because this is a category that can be modeled with optics. So it's a very general kind of machinery. And unlike lenses, it does not assume a Cartesian category. It assumes merely a symmetric monoidal category C. So remember, lenses assume a symmetric monoidal category C plus homomorphic supply of comonoids. But optics just require a symmetric monoidal category C. So optics are quite similar to lenses. So the objects are going to be pairs of objects in C. But amorphism is going to be something slightly different. So it's going to be a triple. We're going to choose an object in C, which we think of as the memory, as the thing saved in between the forward and the backward pass. So we're going to have our forward pass produce an output that also saves some memory that we're going to consume when we take the backward pass. And this added level of generality then allows us to A, model more efficient representation of lenses, and B, allow us to model things that aren't necessarily Cartesian. Yeah, optics compose in a pretty straightforward way. Like the idea is this: you have some process, you save two states, so you save two states, and you consume them all, collect them all on the way back. And there's a way of defining them, which I might actually skip, given that we're short with time. But yeah, you can unpack what optics are in set. And you can show that really optics are, when your category is Cartesian, optics are going to be isomorphic to lenses. So given an optic, you can transform it into a lens, and given a lens, you can transform it into an optic. But very interestingly, they allow us to do more. So something that's quite now in the works and that is being developed is this categorical framework for modeling probabilistic reasoning using the same sort of constructions that are used to model backprop, which is extremely fascinating. And it's still in the works. It's still theories being developed. So here's a paper that models optics in this Finstock category of agents reasoning in this way. My personal motivation for optics is even deeper, well, deeper in the sense of too categorical. It turns out that they allow us to reason about like practical aspects of their implementation. So I have a preprint on arXiv talking about space-time trade-offs, and it turns out many of the things are invisible to one category theory, but when you go to this two categorical level, which we're not going to go into this course, you get to see a lot of very, very cool stuff. Optics, and this is yet another very recent paper, which is why we're not really talking about this in depth. This is a current area of research. You can model value iteration from reinforcement learning using optic composition. So this is insanely interesting. And likewise, you might have heard people when they talk about probability and Bayes' law sometimes refer to it as the chain rule. This is a statement that can be made precise using category theory. So you can have the same categorical construction instantiated in a probabilistic category or in a, say, Cartesian category and get the corresponding chain rules that behave either probabilistically or compute gradients. But as I say, this is an open area on research, not something we're elaborating in this course, but something if you're interested, you can peek at these papers. Yeah, this is bringing us to the end. So we've seen how category theory gives us this very rich language for describing processes found in neural networks. So we can model not just sequential processes, as we've talked about in the first lecture, but processes that run in parallel, processes that copy information, that aggregate information. And the most important thing was talking about the way all of these constructions interact with each other. That's why we have all the axioms, and that's why we're being very stringent about what laws are satisfied, because they tell us something interesting about the semantics. We mentioned these monoidal categories with supplies of monoids, comonoids, but there's many more that can be found in the literature. And I hope we've conveyed that with lenses and optics, you can model this bidirectionality. Really, it's a canonical data structure for bidirectional transformations. And anytime you have something that goes forward and backward, you might have a lens or an optic at hand. So I think this is where I'm going to stop and thank you for your attention.
Okay, thank you very much for the lecture. I don't think we have any open questions.
So I see a question. I've seen a bunch of questions. So I'm happy to take them now. I think there were either answered or not. I see a question now. What is optic C? Are there cases in which applying the optic construction yields a fixed point? That's an amazing question. I pondered this for a while. I don't have a satisfying answer yet. Yeah, that's what I can say. It gets really hard to model because you have an optic has a forward and a backward pass, but now if you're modeling optics, then your forward pass is itself an optic. It gets very hard to think about.
Can I ask a question?
Yeah.
How can you do the backpropagation functors also manifolds, and like how does the bundle structure show?
So yeah, this you might have seen a very small footnote on one of these slides. Let me just go back. This is back in lenses. Right, it's here. So there's a very small footnote saying that the kinds of lenses we have defined here are actually can be generalized in a different way. So these are constant and non-dependent lenses where it doesn't matter where at the point we're at every point in our space, the space of changes, the options where we can go are the same, are isomorphic. But that's of course not the case with manifolds, which are curved. Turns out that can be modeled with dependent lenses, which is yet another way to generalize them. So that's the construction to look at. And I think this should be a link and that can be clicked.
Great, thanks.
I think I saw questions before that disappeared.
There's a new one.
Yeah.
Yeah, it's from Eva. It says, I've read in your blog that there is a practical difference between using optics and lenses. Could you elaborate on that?
Yeah, so what it turns out, which was quite surprising to learn, is that you might have heard of gradient checkpointing as a method of computing, of implementing automatic differentiation. So gradient checkpointing is a method that is often used when you have a very big network and you cannot store it in memory. So you want to just redo a lot of computation so you trade memory for time. You do a lot more computation, but you use as little memory as possible. It turns out lens composition implements gradient checkpointing, full stop. To model different kinds of implementations of automatic differentiation, you can use optics, and they are actually quite versatile when it comes to this efficiency aspect. So in addition to modeling gradient checkpointing with lenses, you can do other things which are more efficient, which use up more memory or less time. And so this is the main difference between optics and lenses, other than the fact that optics are used in a much more general setting.
Can I ask another question? Forward mode, auto-diff. Can we also see that as a lens with two arrows pointing forward?
Yeah, exactly. Except in the categorical literature, for some reason, this is not called a lens. So if lens has maps going forward and backward, this is a lens. This is called a chart. So you can model it, and it has two maps going forward. So it would have, if we go back to this slide, here, a chart would be something that has a map like this, and then this map on the bottom also goes forward. So this is, I think, another question that was in the audience. Why are these concepts named lenses and optics? I think the naming at this point is going haywire, and there's like all sorts of different people have called things kaleidoscopes and prisms, and for some reason these are called charts. So the naming might not be the most intuitive, but yeah, there is a way to model forward mode AD as well.
Thanks.
I see a question, if optics are more general, does that mean that there is a more general notion of backpro that evolves a functor from C to optic C? More concretely, how much of the story of backpropagation can be recovered in non-Cartesian setting, e.g. when dealing with tensor networks? This is a question I'd love to know the answer to, and I suspect a lot. There has been some work showing that you can do differentiation in merely a monoidal category under the name of monoidal reverse derivative categories. This might be quite an advanced paper if people are just starting out, but I would be happy to understand the answer to this. And yeah, this is yet another open question.
Okay, so from Matthew Pug, and I think this can be our last question. It looks like lenses and optics can be used to express computable models. Does the composition and monoidal product of lenses have any bearing on program optimization?
That is an interesting question. So I don't know of any concrete work doing this. So yeah, there's a lot of things that are coming to mind which are tangentially related. So there's been some work on compilers, on composing compilers using sort of this kind of structure called the compiler forest, but this is not really doing about program optimization. So unfortunately, I don't know. Maybe this is a question to ask on Zulip. There could be people to know. Yeah.
Okay, I think in the interest of time, we can end here. And as Bruno said, any questions, comments, or resources you have, post on Zulip. And yeah, thank you very much for coming.
Yeah, thank you very much. And yeah, just